Hello, everyone, and welcome to another episode of Adventures in Algebra. Today, we are going to be talking about logarithms. So, logarithms are special because they're designed to do something very special, and they're also hard to spell. So, log a rhythm. Well, specifically, we're going to be doing logarithmic functions. So just to keep you on the path of what we've been up to so far, in 9.1 we learned about exponential functions, and then in 9.2 we did inverses. So specifically, logarithms are going to be so that we can undo exponentials. Let me be more specific about what I mean by that. So suppose we want to know an exponent, like you invest, let's say $1,000, compounded monthly. Oops, that's a H. At, I don't know, what do you want to pick? Let's do like 6% because that'll make this easier to calculate. Here we go. And you want to know, when will my money double? So to write this out, what we'd do is we'd say, okay, I know my amount. It's $1,000 times 1 plus, now I need my percentage, 0.06. Remember, we do it as a decimal over my number of compounds, which is 12 in a month. And then 12 to the time, and I don't know the time. That's the thing I'm going to not know here. I want to know when it's double. And double of 1,000 is 2,000. So I'm going to take this and I'm going to try to solve for the thing I don't know, when. So hopefully when keys you into the fact that this is going to be time. So I'm going to divide by 1,000 on both sides because that'll take care of that 1,000 out front. And then you'll have, oh, let's do red. 1 plus, if I take 0.06 and divide it by 12, I get 0.005. I'm just trying to simplify this so I can try to get to the unknown, that 12t. 2,000 divided by 1,000 is going to be just a 2. That's looking good. And then it looks like inside I can do 1 plus that, and that'll be 1.005. 12t equals 2. And right over here I'm done. I can't really do anything. I can't get any farther because, like, well, how do I get to t? Because we don't have any tools that do that at this point. Oh no, sad times. And, algebra to the rescue, essentially. So what I need to do is I need to figure out, how do I get to an exponent? And it started out as an exponential functions, just to kind of remind you. We did stuff where we're like, I need to take my existing exponential functions, b to the x, and I need something that when I do it, I get x. Yeah? That's where we're at and what our goals are. Okay? So if we think of this as y equals bx, remember our tool for undoing stuff? Like, oh, what do I need? I want to undo it. I want to do the opposite. Well, I need an inverse. That's what we just learned in 9.2. So the first step is switch x and y. And then you're like, boom, and now solve for y? Huh? Stuck again. Nothing really does this. So we need something new. We need a new tool. And logarithms to the rescue. Here we go. So here's a new definition for you. So logarithms are literally going to be defined so that they get you exponents as their output. So we're going to have x be something greater than 0. Has to be positive to do this. And b our base, so it's got to be greater than 0, and b can't be 1. Nothing new there. Bases are like that. We're going to define or create a new thing called a logarithm. Y equals the log base b, so you put little b down below, of x to b, the same as b to the y equals x. So when you look at this, you have to be careful about how this lines up. Notice where the x is in here, it's in the input or putting into the variable, and over here, it's the output. Whereas Sorry about that, I accidentally paused. When I look at the y, here it's the output and here it's the input. So it is switching, it is doing inverse. It is doing the opposite. So literally our logarithm, base b, the function, this should have been in black, oops, because it's still part of the definition. The function, f of x equals the log base b of x is called the logarithm base b. And how we're going to think of logs, and this is just a tip to help you out with this, what logarithms are going to do is they're going to ask you a question. So put like hearts and stars around this. They ask you, what exponent of b produces y? Or sorry, produces x. I'm writing this backwards. It better be y. Hold on. Come on, eraser. I hope I remember to erase this part. It's y! I know this question seems weird right now, but you're going to hear me do this later, and it will absolutely help you do these. So first off, I want us to focus on this step right here. That highlighter looks horrible. Let's try that again. This step right here. Taking these two and then rewriting them. So we're going to focus on how can I take an exponential and then write it as a logarithm, and then vice versa. How can I take a logarithm and write it as an exponential? That's the first thing we're going to practice because it's going to help us solve these and understand how they're built. So be thinking about that as I do this next example that is totally not going to fit. Well, examples, because, you know, I can never do just one. We're going to write each exponential as a logarithm. So I'm going to write some things we already know that are exponential. So for instance, we already know when I take 3 and raise it to the 4th power, I get 81. So what I'm going to do is I'm going to write the same thing but as a logarithm. So for a logarithm, the base has to be the same. So since the base of this exponential is a 3, it's going to be a 3. And I have to put something in here so that when I raise 3 to the power of the output, because the output for this is going to be the exponent, 4, I get what's inside the parentheses. So it's 81. So again, what exponent of b produces x? It's y! We're doing it backwards. So when you look at the resultant from this, what you get on the other side of the equal sign, it's always going to be the exponent from the previous exponential. Logs produce exponents. Or you should say, logs output exponents, which is exactly what we need. Remember that t was in the exponent. I got to figure a way to get to it. And this is the first step in doing that. Let's do another one. Let's do b cubed is 8. So we're going to write this as a log. So in this one, my base is just b. My exponent was 3. And so in the middle, I have 8. So I need something when I do the logarithm of an unknown base, I get 8. Or b to the 3rd power, because the exponent is the output, is 8. I'm sure you can guess what b is. Yes, we will doing some solving later. Not yet though. Let's do this last one, and then we'll convert the other way. So we want to do e to the y is 11. Remember, e is just the natural base coming from letting your number of compounds get hugely biggy. That doesn't sound like words. So here we go. So this is going to be the log base e of what goes here? 11 is y. Remember, your output needs to be the exponent. So it essentially switches what you think should be happening here. Logarithms are going to do the opposite. Let's do some ones where we go the other way. So this time, rather than writing the exponential as a logarithm, we're going to write the logarithm as an exponential. write the logarithm as an exponential. So we're going to go the other way. Here we go. So suppose we have 5 is equal to the log base 2 of x. Let's rewrite that. So base 2, when I raise it to the 5th power, will be x, because the log says, hey, what power of 2, because that's my base, will give me x? It's 5. So 2 to the 5th is x. Remember, logarithms output an exponent. Let's do 2 is equal to the log base 4 of 16. So we're going to rewrite this. 4 outputs the exponent, so 2, that's my base, is 16. Oh, it is 16. Yay! I just realized I could have done this one up above. You can do what 2 to the 5th is. If you take 2 and you raise it to the 5th power, you totally get 32. So we could have taken this one even further and said, oh yeah, it's 32, dude, because like that's what that is. It's fine. I can't believe I didn't do that. Whoops. We're going to do the log base 5 of 18 is y. Why not? Let's rewrite this as an exponential. So remember, I'm going to take base, it's 5, that's where my b value is, and then remember the output is the exponent, so it's going to be 5 to the y is 18. And I can't take that one any further. So there's some examples of how you can rewrite logarithms into exponentials. So keep in mind, when you're doing a logarithm, that output from the logarithm is an exponent. So that's how you can convert it into an exponential. We're going to use that to solve some things later. Okay, so let's take a little interlude into the special bases. Right. So there's 2 types of special bases. The first one is called the common log, also known as a birch. Just kidding. Don't worry, there's plenty of log jokes coming. I'm sure they're going to make you saw logs. I couldn't resist. Okay, so if we're doing a logarithm that's... No, I don't want to do that, thank you. That's base 10. We just write like just log and then of x. So the trick here is if it's base 10, they just leave off the base. So like if y, that's a very fancy looking y. Why is it fancy? The log base, oops, it's missing, of 40 is just log base 10 of 40. And the reason this is because there's many things that we do out there in the universe that are log base 10. Sound follows a log base 10 system. The pH scale of water follows a log base 10 system. I already said sound, oops. Volcanoes and earthquakes follow a base 10 system. Tornadoes don't though, which is interesting. And then a lot of the things they measure in space follow a base 10 system. So since it shows up so much in nature, they're just like, this is very common. Let's call it the common one and just drop off that 10. So anytime you see a log with no base, you should be like, that's 10. Okay. The next one is called the natural logarithm. And this one was done by the French, so don't judge. Natural log. So if your log is base e, I just wrote is twice. It's called the natural log. And so we write it a little differently. So if we write y is equal to ln of 17, that's going to be the same as the log base e of 17. So the funny thing about this is that it's in French, it's logarithmic natural because that's the order in which the verbs and adjectives go in French, and that's why it's ln and not nl. Well, that, and if the other one looks like log, shouldn't the L go first also? It just makes sense. I'm going to use these special bases to do some calculations. So if there's no value, you're going to call it 10. If it's an n there and not a log, no, then it's base e. Now you may remember that e is the natural base that arises from doing compound interest, so it makes sense that they would call this the natural log. Let's use this to do some calculating. So we're going to come up with numerical answers this time. Calculate, and that's it. That's my directions. I believe in you. It's going to be very simple. Let's do the log base 5 of 5. Okay, so I'm going to write what this is and then explain why. This is going to be 1 because I want to ask myself, what power of 5 will give me 5? Well, but to the first power. This is because when I do 5 to the first, I get 5. Remember, this is asking me how many powers of 5 do I need to get 1? To get 5. I just said that bad. Let's do another one to make sure you're on the same page. Let's do the log base 5 of 25. Now, hopefully you know something equal to 25 that's 5 to a certain power. And hopefully you're yelling at the screen right now, it's 5 squared, lady. Please stop being crazy. Yes, it is 2. And that's because when I square 5, I get 25. Hopefully this is looking like the conversion. Another way you can think about this is if I did the log base 5 of 25 and rewrote it as, well, I'm going to do the log base 5 of 5 squared because 5 squared is equal to 25. Well, then you can see very clearly, oh, well, what's the exponent? It's 2 because this is asking me the question, hey, how many powers of 5 do I need to make 5 squared? Well, you need 2 of them, lady. It's a 2. I don't know why I keep calling myself lady today. I'm feeling like it's a terrific day to be a lady. I don't know. My basement flooded, so I'm good. Why did I even bring that up? Let's try a little bit of a harder one. Let's do the log base 10 of 100. So I'm going to try the trick I did over here. I'm going to think of 100 as 10 squared. And then I'm just going to write 100 because it's fun. Squared. How many powers of 10 do I need to make 10 squared? Oh, I need 2 of them. It's a question. Think log as a question. All right, let's try a slightly harder base 10 one. It's slightly harder because I meant to not write the base 10 and hopefully have you notice, ooh, it's base 10 of 10,000. So much bigger. So you might want to ask yourself, okay, how many powers of 10 do I need to make 10,000? And you're like, it's squared, it's 100, and if I square 100, I get 10,000s. That's square of a square, or 4. So the answer to this is going to be 4. How many powers of 10 do I need to make 10 to the 4th? 4 of them! And if you're real confused, go do 10 to the 4th. It's 10,000. That's the other way to think about it. So if you're scared, write it as an exponential. 10 to the question mark equals 10,000. And then figure out what the power is going to be. In fact, that's not a bad move at all. Let's do the log base 5 of 125. We're back to 5s again for some reason. Now, hopefully you recognize 125 as a perfect cube, so then you're like, oh yeah, that's 5 to the 3rd power, so this is just the exponent, it's 3. I hope you're seeing how logarithms are going to get you exponents off of this. Let's do a slightly weirder one. Let's do the log base 125 of 5. So when I first saw this one as a student, I was like, oh man, that's a little bit insane. Let's think about this. So the reason this top one works is because 125 is 5 cubed. Down here, I want to go the other way. So I essentially want to solve for 5 because that's my input into the log right here, yeah? So think about doing the cube root of both sides, or 125 to the 1/3 power is the same as 5 cubed to the 1/3, which will be 5. Is, multiply these two together and you'll get a 1, which will be 5 to the 1st. So then hopefully you look at this and you're like, I got it. This is going to be 1/3. If you don't like that, you can also rewrite it as, well, the log base 125 of the cube root of 125, because the cube root of 125 is 5. And then you're like, aha, it's the 1/3 power, because now these are the same base, 1/3, because we did fractional exponents recently in chapter 8, which is fun. Let's do another one. Where am I at? I just did that one. Ooh, here's one of my favorites. Let's do the log base 701. Now, we've said it before, and we'll say it again. I know that when I do certain things, I will get 1. Let's talk about that. I don't know what the result of this is. Let's just call it question mark so I can rewrite this as an exponential. So you're like, I don't know how I'm going to get 1 out of 7. That sounds insane. Remember, logarithm's another question. How many powers of 7, I don't know, do I need to make 1? And then hopefully this answer screams out at you, ooh, anything to the blank power is 1. And then you're like, oh man, I know this. It's 0. Because 7 to the 0 power, well, really anything to the 0 power is 1. And so this is something that every log will have in common regardless of base and regardless of input. If I raise it to the 0 power, regardless of base, not input. If I raise it to the 0 power, I'm going to get 1, which means every log, any base, when I do 1, will give me 0. What am I on? F? Yay! All right, let's do the log base 3 of 3 to the 4th. This one should be darn easy. Why did I put this one here? That one should have been earlier. It's 4. Self-judgment increasing. Why did I pick up the 0? I don't know. E, B, C, D, E, F, G. I just sang the song to get this. I judge. What's the natural log of 1? We just saw this. What's any log, any base? If I want 1, its exponent better be 0, because e to the 0 is 1. Remember, when I see the natural log, base e. E! That was for fun. What am I on? H? H. Speaking of natural log, what's the natural log of e? Well, hopefully you recognize that e is just to the first power, because we don't usually write the exponent on this, just like earlier when I had 5 to the 1, it looked weird because we would just think of that as 5. So this is saying how many, natural log, base e. So how many e's do I need to make e to the first power? Well, I just need one of them, because, and this is going to be the silliest thing I write, e to the first is e. I don't like that. That looks wild. Let's try it again. I can definitely tell which letter is next. What's the natural log of e to the 7th? Remember, think of natural log as a question. This is base e, so how many powers of e do I need to make e to the 7th? Well, I need 7 of them. Because, oh no, this is another bad one. E to the 7th is e to the 7th. Oh, why do I do this to myself? Hopefully you're seeing something magical happening when I do stuff at the same base. Just like when I was doing the log base 10s to 10 powers, like it was nothing magical. What am I on? J? Here's a fun question for you. What's 5 to the law of base 5 of 12? Now this one might blow your mind. Remember, we earlier said that, hey, logarithms and exponentials are inverses of each other. So right here, what I was really doing is I was doing two things at the same base that were inverses. So of course, they should pop out x. In this case, x was 7. Here, two things at the same base. They should undo each other. I'll just get 12. Why? Because 5 to the x, and that's not how you spell the word and. The log base 5 of x are inverses of each other. They undo each other. Let's see another one of those. What am I on? K? Let's see, I want to do 10 of the log of 17. I had 17 pop up a lot today. Speaking of, these are the same base. They undo each other. They're both base 10. I'll just get 17. Now, you don't have to write the because stuff. I do, so that when I look back at my notes, it makes sense. So I'm just writing them as functions. These are inverses, and inverses give you back what you started with. That doesn't look like a word. Are inverses. Love it. Because that's the magic of logarithms. Okay, so we've done a bunch of stuff. I want to make a little summary of all the common stuff we've seen so far. So we're going to call these common log properties. So what I've noticed so far is if I take the log of any base of 1, I get 0. That's one we already observed. Same thing for natural log. So don't think that one's special. comma. If I do the log base b of b to a power, I just get that power because logarithms are questions about exponents. Similarly, if I do the natural log of e to anything, that was supposed to be a bigger parenthesis, I get that thing back. My x's are looking rough. Now the last power we just saw is that since logs and inverses are inverses of each other, I can also go the other way. If I do an exponent raised to the log base b of something, I just get that thing back. And of course, because that's who I am, let's write the same thing using the natural logarithm, because sometimes that one throws people. So anytime you combine a logarithm with its inverse function, you just get x back. So what I really should do is write this with an x. Sorry about that. I should have done that from the beginning. Oh yeah. In case you weren't sure they were inverses of each other, let's do some graphing. Come on. So we're going to graph together. Oops, this was supposed to be an example. We're going to do f of x equals 2 to the x, and I'm going to put it over here. And well, g of x is not going to fit, so I don't know why I tried. And g of x is the log base 2 of x. So I'm going to do some graphing of this. Here we go. So first up, I'm going to do some tables of values. I'm going to do f first. And just like you've seen me do many times, I'm going to be kind of uncreative with my choices. I'll do -2, -1, 0, 1, and 2. And we did this in our, well, 2 videos ago with exponentials. So I'm going to do this kind of fast. 2 to the -2 is going to be 1/4. 2 to the -1 is 1/2. 2 to the 0 is always 1. Well, anything to the 0 is always 1. 2 to the first is 2. 2 to the second power is 2 squared, which is 4. So if we were to graph this guy, this should be big enough, I think. 1, 2, 1, 2, 1, 2, 3, 4. Yeah, it goes up to 4. Okay, good. Here we go. So at 0, we're at 1. At 1, we're at 2. At 2, we're at 4. And here I got to do 1/4, which I, or no, 1/2, which I can actually do fairly accurately. And then 1/4 is probably like right here. And hopefully you remember something about how the exponential looks. And remember, never can get 0. Now, that's pretty good. Okay, I definitely should trim that down time-wise though. All right, here's the thing. When it comes to graphing a logarithm, you got to pick values you can actually do the logarithm of. So in looking at what I have here, you might be shocked by my choices, but I'm going to pick nothing that is negative. In particular because you cannot do the natural log or any log of a negative. In case you forgot about the definition, it said that your x's got to be greater than 0. So I'm only going to be picking positives and only things I can do the log of. I'm going to start with 4, and then I'm going to do 2, and then I'm going to rather unceremoniously pick 1/2, and then 2 to the -1, which is 1/2, and 2 to the -2, which is 1/4. And you'll see why these last choices are made. So here I'm going to be doing the log base 2 of 4. So it's asking you, how many powers of 2 do I need to make 4? I need 2, because 2 squared is 4. How many powers of 2 do I need to make 2? Well, I only need 1, because 2 to the first is 2. Alright, how many powers of 2 do I need to make 1? Well, that's one of our common properties. It's none of them. How many powers of 2 do I need to make 2 to the -1? Well, -1 of them. How many powers of 2 do I need to make 2 to the -2? I need -2 of them. I meant to do this in a different color. Oh boy. I'm having all kinds of mistakes here. But let's graph this. So x is 4. So I need to make sure I do out to 4. There we go. Alright. And I will need some negatives on the y scale. There we go. That looks good. I want to do this in blue. So G is in blue. So when x is 4, y is 2. 4, 2. When x is 2, y is 1. So at 2, it's 1. When x is 1, y is 0, so it's right there. When x is a half, so right about there-ish, it's -1. When x is 1/4, so here-ish, is -2. Hoping you get an idea of the look of the natural logarithm, because it looks like this. Now, if you're looking at this and thinking, this looks kind of magical, I agree. I've been waiting to use this pen. They are reflections of each other. So they're reflected across the line where y equals x, because when you are doing inverses, you're switching x and y. F is g reflected over y equals x because they are inverses. They switch each other. So like, look, these two are perfectly across from each other, and these two, and these two, and these two, and I can't quite reach that one. There we go. These two. Oh yeah. And you can do it further up too. Like, it keeps working as long as, like, that looks weird. It works. Kind of fun, maybe. This was just to help you visualize what the logarithm looks like, and it's quite strange. So just like how the exponential can never reach 0 in x, the logarithm can never reach 0 in y. So you can never, you can never input a 0 into the logarithm because you can never output a 0 into the exponential. It'll get really small, but it'll never be 0. Let's do one last step. So just keep in mind, or maybe, I don't know, super hearts and stars and things, remember that since an exponential can never reach 0 as an output, for your input you can never get 0. So for logarithms, x is already, or your input always has to be greater than 0. Let's just write input because it might not be necessarily x, it might be something more complicated as we're about to see. The input's got to be greater than 0. You can't do the logarithm of a negative. It don't work. Speaking of, let's talk domains. Let's use that. So we're going to find the domain of each of the following. So we're going to do f of x is the log base 2 of x minus 3. So as I just said, when you're doing a logarithm, whatever you've got going in here, it can't be negative. So x minus 3 got to be greater than 0. So we'll add 3 to both sides. X has got to be bigger than 3. So we would write our domain in one of our two notations of choice. I could do set builder and say I want my x's so that x is bigger than 3. Or if you don't like that one, because I know a lot of you don't, you can write it as an interval. So I want to go from 3 all the way up to infinity, because really you should be thinking of this as any x bigger than 3. Let's do the same thing, but with a slightly different function. Let's do g of x is the natural logarithm of 5 minus x. So again, same difference. I want the stuff inside the logarithm. This time it's base e, but doesn't make any difference. Still a logarithm. Gotta have, oh, it's not x, it's 5. 5 minus x be greater than 0. So be careful. Watch your signs on this one because it can cause some problems. I am going to elect to add x to both sides because that will prevent me from having to deal with that. So then I'll just have 5 on this side is greater than x. So when you read this, you want to think of this as 5 is greater than or equal to any number that's in my domain. So the largest it could be here is 5. So when I go to write my domain, if I'm using set builder notation and I'm feeling super lazy, I would just write x less than our 5, because that's what it is. It's small. 5 is the biggest it could be for our numbers x. So this is the same as x is less than or equal to 5. Or you could write it as an interval. So everything smaller than 5, so negative infinity, and the biggest it could be is gets up to 5. And that's it. So, to recap what we learned today, we defined what a logarithm is. We used it to do some calculating. We did some converting back and forth to exponentials. And then we used it to do some function stuff. So it's not going to end here. I still didn't answer that first question we had of, oh my gosh, how do I get to the exponent? So in order to do that, we're going to need some more properties of logarithms. So we're going to have to do some more fixing on this, but I feel like this is long enough as is, so we're going to stop. In the next section, we're going to be focusing on what are the properties of logarithms that I have that I can use to solve stuff, and that's going to be our whole goal. So look forward to more logs next time. Maybe we'll try some different wood, like, I don't know, pine.